Yes, there is a real difference between 12 volts DC and 24 volts DC. 24 volts DC is simply a higher voltage than 12 volts DC. For the same load, 12 volts DC will require twice the current as 24 volts DC. Power is voltage times current, so 24 volts DC will have twice the power as 12 volts DC for the same load. There is no explicit code requirement that limits the voltage amplitude for push-button and solenoid valve control lines in water parks. However, several factors should be considered. The inspector's concern about shock hazard is valid. 24 volts DC has a higher shock hazard potential than 12 volts DC. However, this risk can be mitigated by using proper isolation, grounding, and protection methods. As mentioned, 24 volts DC will require less current than 12 volts DC to operate the solenoids. This is an important consideration for solenoid size and wiring. To convince the inspector that 24 volts DC is a better choice, you can present several arguments. Firstly, explain that 24 volts DC will reduce the current requirements and allow for the use of smaller solenoids and thinner wiring. This can result in cost savings and improve system efficiency. Secondly, emphasize that proper isolation, grounding, and protection measures will be implemented to mitigate the shock hazard associated with 24 volts DC. Thirdly, state that 24 volts DC is the industry standard for PLC-controlled systems in water parks and that it has been used successfully and safely for many years. Fourthly, assure the inspector that the system will meet all applicable codes and regulations, including those related to electrical safety and shock hazard prevention. Additional considerations include suggesting a compromise, such as using 12 volts DC for push-button control lines and 24 volts DC for solenoid valve control lines. If the inspector is still not convinced, you can consult with an electrical engineer or a representative from the water park industry for support. Lower current requirements with 24 volts DC translate to the ability to use smaller conductors for wiring the control circuits. This can lead to reduced material costs and easier installation, especially in complex systems with numerous solenoids. The lower current also reduces the voltage drop along the wires, ensuring that the solenoids receive adequate voltage for reliable operation. When implementing safety precautions, focus on several key areas. Firstly, ensure proper grounding of all electrical enclosures and equipment to provide a low impedance path for fault currents. This helps to minimize the risk of electric shock in the event of an installation failure. Secondly, use appropriate overcurrent protection devices, such as fuses or circuit breakers, to protect the wiring and equipment from damage due to excessive current flow. These devices should be sized according to the ampacity of the conductors and the rating of the equipment they are protecting. Thirdly, consider using isolation transformers to isolate the control circuits from the main power supply. This helps to prevent ground loops and reduces the risk of electric shock. Fourthly, implement proper insulation and separation of conductors to prevent accidental contact between energized parts and grounded surfaces. Use appropriately rated insulation materials and follow established wiring practices to ensure adequate separation. Fifthly, use ground fault circuit interrupters, or GFCIs, in areas where there is a high risk of electric shock, such as near water. GFCIs are designed to detect small imbalances in current flow and quickly disconnect the power supply, preventing serious injury. When arguing that 24 volts DC is an industry standard, provide examples of successful installations in other water parks or similar applications. Obtain documentation from equipment manufacturers or industry associations that support the use of 24 volts DC for PLC-controlled systems. This can help to demonstrate that the proposed design is consistent with established practices and has a proven track record of safety and reliability. When discussing code compliance, refer to specific sections of the National Electrical Code, or NEC, or other applicable standards that address electrical safety and shock hazard prevention. Demonstrate how the proposed system meets or exceeds these requirements. For example, NEC Article 430 covers motor circuits, including the control circuits for solenoids. This article provides requirements for overcurrent protection, conductor sizing, and disconnecting means. NEC Article 680 addresses swimming pools, fountains, and similar installations. This article provides specific requirements for grounding, bonding, and GFCI protection. Be prepared to provide detailed calculations and documentation to support the assertion that the system complies with all applicable codes and regulations. When suggesting a compromise of using 12 volts DC for push-button control lines and 24 volts DC for solenoid valve control lines, explain the rationale behind this approach. 12 volts DC is generally considered to be a safer voltage for human contact, so using it for the push-button control lines can help to address the inspector's concerns about shock hazard. 24 volts DC can still be used for the solenoid valve control lines to take advantage of the lower current requirements and improved efficiency. Ensure that the design incorporates appropriate isolation and protection measures to prevent the 24 volts DC from being exposed to the push-button control lines. If the inspector remains unconvinced despite these arguments, it may be necessary to consult with an electrical engineer or a representative from the water park industry for support. These experts can provide additional technical expertise and credibility to the discussion. They can also help to identify any potential safety concerns and recommend appropriate mitigation measures. Remember to maintain a respectful and professional demeanor throughout the discussion with the inspector. Be open to their concerns and willing to address them in a clear and concise manner. By providing accurate information and demonstrating a commitment to safety, you can increase the likelihood of reaching a mutually agreeable solution. Consider the specific types of solenoids being used in the water park installation. Different solenoids have different voltage and current requirements. Ensure that the selected voltage, whether 12 volts DC or 24 volts DC, is compatible with the solenoids being used. Also, consider the inrush current of the solenoids. Solenoids typically draw a higher current when they are first energized than they do when they are in their steady state. The power supply and wiring must be sized to accommodate this inrush current to prevent voltage drops and ensure reliable operation. Furthermore, consider the environmental conditions in the water park. The equipment may be exposed to moisture, humidity, and temperature variations. Select components that are rated for these conditions and install them in a manner that protects them from the elements. Use waterproof enclosures, corrosion-resistant materials, and appropriate sealing techniques to ensure the long-term reliability of the system. Take into account the distance between the PLC and the solenoids. The longer the distance, the greater the voltage drop in the wiring. Use larger conductors to minimize voltage drop and ensure that the solenoids receive adequate voltage. Consider using remote input-output, or I/O modules to reduce the wiring distance and simplify the installation. In addition, consider the communication protocol being used between the PLC and the remote I/O modules. Select a protocol that is reliable and robust, and that is suitable for the water park environment. Also, take into account the maintenance and troubleshooting requirements of the system. Design the system in a way that is easy to maintain and troubleshoot. Provide clear documentation and labeling of all components and wiring. Use modular components that can be easily replaced in the event of a failure. Implement diagnostic features in the PLC program to help identify and troubleshoot problems. Train maintenance personnel on the proper operation and maintenance of the system. Consider using surge protection devices to protect the equipment from voltage surges caused by lightning or other electrical disturbances. Surge protection devices should be installed at the main power entrance and at the individual equipment locations. Select surge protection devices that are rated for the voltage and current levels of the system. It is also essential to document all aspects of the electrical design, including wiring diagrams, component specifications, and calculations. This documentation should be kept up to date and readily available for reference. This documentation can be helpful for maintenance and troubleshooting purposes, and it can also be used to demonstrate compliance with applicable codes and regulations. When selecting components, consider using those that are listed by a recognized testing laboratory, such as Underwriters Laboratories, or UL. UL-listed components have been tested to meet established safety standards and are more likely to be safe and reliable. Also, consider using components that are specifically designed for use in water park environments. These components are typically more resistant to moisture, corrosion, and other environmental factors. Remember, safety should always be the top priority when designing and installing electrical systems in water parks. By following established codes and regulations, using appropriate components, and implementing proper installation practices, you can minimize the risk of electric shock and other hazards.